Ohanian 6.86 describes a box, and it has a mass M, with M equals 1.5 kilograms, and it's sitting on a flat surface and being pulled horizontally by a spring. You're pulling the spring off to the right. They give you the spring constant, K equals 1.2 times 10 to the third newtons per meter, and they give you the coefficients of static and kinetic friction between the block and the table, 0.60 for static, and mu k, which has to be less than or equal to mu static, equals 0.40. Then ask a series of 3 questions. Question A is, by what amount do you have to stretch the spring to get the block to move? Okay. Now that means you have to overcome the force of static friction holding the block constant, and that means that the force you pull with, the spring pulls with towards the right on the mass has to be greater than or equal to the maximum force of static friction holding the block in place. Okay. So the force of the spring, just putting that into equations, has to be greater than or equal to mu Sn, where that'll be the maximum force of static friction. Now we know that N, if you look at the vertical direction and say the sums of the force in the vertical direction have to be 0, that will just give you N equals mg. So I'll write that down. And then the force of the spring is just going to be kx. It's to the right, so I'll make it positive. K is the spring constant that you were given. And to have it just barely able to move the block, it has to be just slightly greater than, or greater than, but I'll just make it equal to mu Sn, which is mu S mg now. And we can solve this for x. X equals mu S mg divided by k. And just plug in your various numbers. Mu S is 0.60, m is 1.50 kilograms, acceleration of gravity 9.81 meters per second squared, all divided by the spring constant, which is 1.2 times 10 to the third newtons per meter. Okay, and plug this into your calculator, and you should find 7.4 times 10 to the minus 3 meters. So that's the amount by which you must stretch the spring. Pull it out an additional delta x of 7.4 times 10 to the minus 3 meters, and the block will start moving. That means you've overcome static friction. Okay. Well, that leads us to question B, which is what's the acceleration of the block if you maintain the same stretch of the spring? Now, that's saying the same thing as maintaining the same force, because if you maintain the stretch and K is the same, you're keeping the force of the spring the same, but the force of friction is lower because the coefficient of kinetic friction is less than that of mu static. So we can write down all the forces in the x direction. Maybe I should have said that this will be my positive x direction. Okay. All the sums of the forces in the x direction equals the force of the spring to the right minus the force of kinetic friction to the left. Okay. And that's just going to be equal to kx is the force of the spring, and it's pulling to the right. Kinetic friction now is mu k instead of mu s mg, and those have to sum to give you mass times the acceleration. And we can solve this expression for the acceleration. A is equal to kx over m minus mu kg. And again, you just plug in your various numbers, 1.2 times 10 to the third newton per meter times 7.4, the same stretch we had up above, that we solved for up above, divided by the mass, which is 1.5 kilograms, minus the coefficient of kinetic friction, 0.4, and g, 9.81 meters per second squared. Just squeeze that in there. That's equal to 2.0 meters per second squared. Done. And I can imagine somebody asking whether you should show the free body diagram, and I suppose maybe I should have. So let me just do that now. A little bit late. So we have a mass m, normal force up, mg down, force of the spring pulling to the right, and the force of friction pulling to the left. And my coordinate system was X and Y. So if I was being really careful, I'd have done that up front, but the calculation here was so easy, I didn't bother. And if this was an exam, you wouldn't have to bother either unless we gave you instructions to show the free body diagram or told you to solve the problem showing every step that you should in principle show. So in any case, let's move on to part C, which is, okay, if you keep pulling with this much stretch, the block is going to accelerate, which means the speed keeps going higher and higher and higher. What if you want to just maintain a constant speed? Okay, how much stretch should you have then? Well, V equals constant is just another way of saying, oh, I want zero acceleration, and we already have an expression for the acceleration and how it's related to the forces. So that means I just want to use this same concept, the sums of the forces in the x direction, the spring force minus mu k mg, but now I said equal to 0. Okay, because I know the acceleration, I'm no longer trying to solve for it, but now I'm trying to solve for x. What's the stretch of the spring? Just a little bit of algebra. Plug in the numbers. 0.5 kilograms, 9.81 meters per second squared divided by the spring constant equals 4.9 times 10 to the minus 3 meters. Quick check. That's less stretch than I found up above, which should be reassuring. It takes less of a stretch of the spring to keep it moving at constant speed than it did to get it moving in the first place. That's it.